Hello YouTube, this is Dazza the cameraman. Today is Tuesday the 17th of September 2013 and I'm pleased to have a guest here, Ian Musgrave, astronomer from Adelaide, South Australia. Welcome Ian, nice to have you with me.
Hello Dazza, it's great to be here.
Thank you. Can you tell us a little bit about your interest in astronomy and what you're doing, please?
My interest in astronomy goes back to when I was quite small. I used to lie out in my backyard with my dad's binoculars. Where we lived at the time was very close to the bush, and you'd have this beautiful sky. Unfortunately, now it's all covered in light pollution, so I just loved the sky. When I was older, my dad helped me build my very first telescope, which is still sitting in the shed, and I've been a comet tragic for as many years as I can remember. I remember taking my then girlfriend out to see Comet Halley when it came round, and got her up to see the comet, and she said, "It's a fuzzy dot. You got me up at 4 o'clock in the morning to see a fuzzy dot." She wasn't impressed, but I've been following comets for many years now. I follow them with binoculars, I follow them with my telescope. I'm a member of the Stereo Hunter group that tries to identify new comets, mostly Kreutz comets, in images from the stereo spacecraft. And I have an account with the iTelescope group where I do a lot of comet astrophotography that way.
Right, very good. Well, it certainly sounds like a very similar story to a lot of amateur astronomers who started off at a very young age, and their hobby and their interest has grown from there. Now, you also have a very interesting Astroblog. I'm just going to change the screen so we can see that on screen. And this is Ian Musgrave's Astroblog, and I'll put a link in the description area. And Ian has produced this very interesting article about Comet ISON, which he has called Comet ISON FAQ for the Perplexed. So I'll just go back to you there, Ian, and if you could tell us some more about that, please.
Yes, well, as with all bright comets, there's a lot of excitement around, or potentially bright comets, there's a lot of excitement around them. And we've saw this for Halley, we saw this for Comet, which turned out to be a bit of a dud in terms of what was expected, but it actually turned out to be a very important scientific comet. It was actually a really nice little comet. It wasn't fantastically bright, but it was really quite nice. And so with virtually every bright comet that comes around, you get this really intense interest. But you also have all this misunderstanding and misapprehension about comets, which goes back to the 18th, 19th centuries. The swirling misinformation that came around the bright comets, the great comets of the 19th century, and Comet Halley itself. And so what I've been trying to do is to try and address some of the bigger bits of misinformation that have been circulating on the internet, and try and get people to understand what it is we're seeing and what we'll be likely to see.
Right. Now, you're going to share in your screen at some stage. You can let me know when you want to do that. I'm just going back to your page again so we can look at that. You've got quite a number of questions and answers, such as, so I heard Comet ISON has broken up. Will it hit the Earth? But surely the comet's encounter with Mars and the Sun will alter its orbit. What if the comet breaks up, and so on? So maybe if you could talk us through some of that, and as I say, when you're ready to share your screen, just let me know.
Yeah. As you may be aware, Comet ISON is expected to be a really bright comet, but there's a bit of uncertainty of exactly how bright it is. Now, we haven't been able to observe the comet for a while because, from our point of view, the comet was behind the Sun. Now the comet's just come out from behind the Sun. As soon as this comet started to come out from behind the Sun, we got all these things happening. The comet was a fizzer. The comet had broken up, and we had things like people posting on Facebook images of the breakup of an entirely different comet, Comet 73P Saxman-Wasserman, claiming this was ISON. So there's a lot of that information, really bad information going around. So the comet, when it first came out from behind the Sun, it was really low to the horizon. and it was very difficult to see because the comet's still relatively faint, and you're trying to look at this very faint object through the murk of the horizon. So it was difficult to get good images of it, and difficult to get good magnitude estimates. Now the comet's getting higher and higher, and we're getting better and better images and better and better estimates. It looks like the comet is pretty much what's happening with it is pretty much what was predicted. You may probably also have heard all of it's going to be really bright, visible in the daylight, etc., etc., etc. The initial ideas that it was going to be really bright came from some very early estimations when the comet had just been discovered. But one of the things that was one of the things that they predicted it might be as bright as the full moon, and we'll deal with that concept a little bit later. But then it was found that it was this was its first time through the solar system. And so the comets that have come into the solar system the very first time tend to brighten very quickly, very early on, possibly because they've got all this frost of things like carbon dioxide and carbon monoxide on the outside, which rapidly evaporate and blast off some dust, and then it settles down. So brightness doesn't evolve in the same way as comets that have been around the sun several times do. And so they redid the calculations, and it looks like the comet's going to be somewhere around about as bright as Venus at its brightest, or maybe a little bit brighter, maybe twice as bright as Venus. And it took a little while before the comet could get high enough above the murk of the horizon for people to see. And it looks like the comet's pretty much on the track for the range of brightness estimates that we were talking about. So at the moment, we can expect that the comet will brighten as it gets close to the sun, to roughly about the brightness of Venus, or a little bit better. It won't be as bright as the first estimates, but it will still be quite bright when it's closest to the sun. But that's when it's closest to the sun. And unfortunately, it gets very close to the sun from our point of view. So it's actually going to be only about a finger width away from the sun at its closest. So when it's going to be brightest, it's going to be really, really close to the sun, and it'll be almost impossible for anyone who hasn't had a lot of experience at looking for objects close to the sun to see it, and even then it'll be quite difficult. I have a little hobby, which is seeing Venus in the daytime. And I can quite often take people and show them how to see Venus in the daytime. And when Venus is really close to the sun, it's really, really hard to pick up, because the bright sky around the sun drowns Venus out. Right now, you can go out and see Venus in the daytime quite relatively easily if you know how to look. But when it's really close to the sun, the bright light around, the bright air around the sun makes it really difficult to pick up Venus. It'll be the same for this comet. But coming as the comet comes in towards the sun, it should brighten up reasonably well. It should it won't be spectacular as it comes in towards the sun, but you'll be able to see it with the unaided eye, and right towards the end, when it's getting close to the horizon, it should be reasonably bright with a nice little tail. I don't know if anyone saw Comet Pan-STARRS earlier on this year. It was a bit difficult to see in the twilight, but if you made the effort to go and look, it was a quite nice little comet. And Comet ISON should be easier to see against the twilight than Comet Pan-STARRS by quite a reasonable amount. And this comes back again to the idea of what we're expecting. So from very early on, there were some early expectations, but those expectations have been magnified by the internet. And whereas somehow they forgot that when the very early predictions came out, they had these "it might be," "it could possibly be," and that's all been shorn away, and just they're remembering the very early prediction and saying it will be, rather than going with what we now know for more refined estimates.
Okay, so we're talking about twice the brightness of Venus, is that right?
Yeah, somewhere between as bright as Venus or twice as bright as Venus. It'll be a very, very nice little comet. And so, but you have these two opposing rumours. One is that it's going to be really, really bright. And again, this is what people forget when we say it's going to be, when they say it's going to be really bright. It's only when it's closest to the sun. They hear this, it's going to be, say, as bright, twice as bright as Venus. I think you'll be able to see it in the evening sky looking twice as bright as Venus. This is only when it's really close to the sun. How it evolves once it gets close to the sun depends. Now, the Comet ISON is what's known as a sun grazer. There's no formal definition of a sun grazer, but it's going to become around about 2.5 solar radiuses away from the sun's surface, which is pretty close. And so it's probably outside the limit for tidal disruption as it whips around the sun, but it'll be subjected to really intense heat. And comets are really quite fragile things. They tend to fall apart relatively easily, as we saw with Comet ISON a couple of years ago. And there was a lot of rumours about ISON and how it would do all sorts of horrible things to the Earth, and it just quietly disintegrated and floated away. Right. A couple of years ago, we had Comet Lovejoy, which came even closer to the sun than ISON is going to. It flipped around. It actually survived for a couple of days past its closest encounter to the sun and then disintegrated. With comets, comets are a mixture of dust and ices, and I say ices deliberately because the ices are a mixture of water ice, carbon dioxide and carbon monoxide ice. And even though and you have this all this material mixed up together, and you might think that ice would just blast away in the heat of the sun, but actually it's a relatively poor conductor, and so it takes a while for the heat of the sun to penetrate into the core of the comet, and it will take some time for the comet to heat up. And so you find quite often these things break up afterwards. The same thing happened with Comet Iosaki, but unlike Comet Lovejoy, which disintegrated completely, Comet Iosaki broke up into a couple of pieces. And what does this mean for Comet ISON? Well, how bright the comet is after it comes closest to the sun depends on a lot of things. We know comets are always brighter after they become closest to the sun, because when they're closest to the sun, it involves boiling off a lot of dust and gas. So if it remains intact, we could expect something that's really relatively bright, quite nice, and it may have a quite decent big tail. If it disintegrates entirely, it might be something like what we saw with Comet Lovejoy. Even though Comet Lovejoy disintegrated it completely, you still had this long tail, this long searchlight-like tail stretching up above the horizon. And on Christmas Day, it was brilliant. You had to get up at 4 o'clock in the morning to see this beautiful tail stretching from below the horizon all the way across the Milky Way up into to the centre of the sky. Absolutely incredible. But if it's like a Kiyosaki, if it breaks up into large chunks, it may release enough dust, become even more brilliant, and have an even more amazing tail than is likely from just whipping around the sun. So there's a number of possibilities, and we can't give really definitive answers now because it depends on whether or not the comet breaks up and how it breaks up.
Okay, Ian, now you're saying that the comets can be rather difficult to predict what they're going to do. So would you like to speak some more on that?
Yes. Well, it's been said that comets are like cats. They have tails and they do what they want. And people have interpreted that to mean that we know nothing about what comets will do, and they're like some cosmic billiard balls zooming around, banging off things. And on the back of that, there's a number of rumours going around the internet that the comet will possibly hit us, that the NASA is deliberately slowing down the simulation that they've made of the comet to make sure it doesn't, so people don't see it hits the Earth. And when we're talking about uncertainty about the comets, we're talking about uncertainty in terms of how bright these things will be, because this relies on things like what the ratio of dust to gas is, whether or not the comet breaks up. These are things we are uncertain about. What we're not uncertain about is their orbits. Their orbits are pretty good. The orbit we have of ISON is determined by more than 3,000 observations by amateurs and professionals over several months. So we've nailed down the orbit pretty well. Well, we know that because we were able to pick it up when it came out from behind the sun. We were able to go straight to where the comet was, and there it was. So the orbit's nailed down pretty well. But the problem with, say, things like looking at the NASA simulation, it's set up to give you an idea of what the comet looks like in one particular direction. So it's very easy for people to, and it's also trying to make slow the comet down around perihelion, so you can see it just instead of going zip, you can see what's happening. So I'd like to play you a little simulation that I've done in Celestia, using the latest orbital parameters that have come out of the Minor Planet Centre, which, for those people who are worried about NASA doing things, the Minor Planet Centre has got nothing to do with NASA. It's all derived from observations of amateurs and professionals who are worldwide, so it's not a NASA thing. So if I'll just bring up the simulation. And I'll put that onto full screen. Okay, this is a simulation that I've done in the program Celestia. Celestia is a 3D space modelling program, and I've started the simulation at the point of time where Comet ISON is crossing Earth's orbit. Now, before I press the button, I want you to notice something that this can be quite difficult to see. But the comet is above Earth's orbit. It's there, you can see the comet there, and you can see way over on the other side of the comet, indicated by the cross there, is the planet Earth. So it's quite a way away from us. Now I'm going to press the button, and you see the comet's going past Earth's orbit, well past Earth's orbit. Now it's going to zip around the sun. I'll do this really quickly, and you can see the tail gets bigger. And it zips away, then goes off and disappears. And you can see at no time does the comet come anywhere near the planet Earth.
Right, so as it leaves, it's actually going to be well above the orbital plane of the Earth, isn't it?
It's going to be well above the orbital plane of the Earth. Now, I'll just stop this video, and I'll know to flip over to Celestia itself. And I've got the time set to now, but I'm just with this simulation. I'm just going to. Can you see it moving around at the moment?
Yes, certainly.
Okay, so we'll put this flat on, so we're looking directly down on the sun there, above the plane of the solar system. You can see the comet. Now, in a lot of the simulations you see, they do these flat views. It's very difficult to see the three-dimensionals.
Ian, can you just point out the comet for us on there, please?
Okay, the comet is the one with the red flashing cross on it. Okay.
Right. Okay.
Over there.
Yes, I'll just position my cursor so we can see it there. Yes.
We can see it's slightly confusing because I can't get rid of the outer planets, but you can see that in this three-dimensional model, the comet's above the plane of the solar system.
Right.
And that's substantially above. Now I'll zoom into the time when it's going to be crossing Earth's orbit. Okay. And there you go, there's the comet. There again, you can see in this, the Earth is very far from the comet. And if we bring it up so that you've got there's the plane of Earth, and the comet's still above the plane of Earth. And then we'll just put it into a bit later, where the comet's now past Venus. You can see that it's now below the plane of Earth, still far away, but below the plane of Earth. And the comet just zooms in, crosses above our orbit, zooms underneath, and then I'll go to that's almost as closest to the. I'm sorry for making the simulation rock around a bit. And you can see the comet's well below, and also notice the tail. See how the tail is pointing down and away from Earth. There's a lot of people are worried that the comet's tail might actually hit Earth, but the tail is always pointing away from the sun, and so as it gets closer to the sun, the tail is actually going further and further away from Earth.
Right, because of the solar wind, the pressure from the sun, it's actually pushing that tail away, isn't it? It's rather like a windsock. So that tail is always going to be pointing away from the sun, even as it leaves the solar system. It will appear to be going backwards.
Yeah, and again, there you see, there's Earth, there's the comet when it's closest to the sun with its massive tail. The tail's pointing directly away, and also the material in the comet's tail follows the orbit of the comet, so it doesn't sort of go screaming away around towards Earth or anything. It will follow the orbit of the comet, so all that material that's coming out will continue around with the comet as it goes around and flip out and go into deep space. So again, the people are worried that on the 14th of January, the Earth will cross the point where the comet crossed above our orbit, and maybe and they're worried about encountering the tail then, but the tail will have been gone for 2.5 months by the time Earth gets there, so there won't be any effect on. I'll just put into the simulation. I'll put into the 14th of. First I'll do the 25th of December, which is pretty close to the time when the comet is actually closest to Earth. And you can see, even though it's actually at its closest to Earth, it's still very far away. It's further from Earth than Venus is. So it's actually reasonably far away. When it's crossing the Earth's orbit, if you look at the flat view, it looks like it's very close to Earth, but it's actually much further away because Earth's further around in its orbit. And you can see the tail still pointing away, and it's flicking away and disappearing into space. And by the time we get to 14th of January, where Earth gets to the point where the comet crossed, the comet's well gone. It's very it's off screen in this simulation. I'll just move it around. So there you are. There's the comet disappearing into space, well away from Earth. So we won't come anywhere near any of the material of the tail. Not that it would matter if it did, because we've actually been inside the tails of comets for quite some time. We were in the 1910 apparition of Halley. We were inside the tail of Halley's comet for a day. In the great comet of 1853, we were in the comet's tail for 2 days, and absolutely nothing happened. People forget that comets' tails are really thin. They look very bright because you're looking through a lot of dust. The dust is really thin, but because there's so much of it, it's reflecting a lot of light back to us. But the comet's tail is a really good approximation of a vacuum, and so people get upset about look, there's cyanogen in the comet's tail and it's toxic. Yes, but again, you're looking at something where you've only got a handful of molecules per cubic centimetre, and if you squash the entire comet's tail down and dumped it in Earth's atmosphere, the concentration of cyanogen would be so small you would not be able to measure it. That's how little material there is in the comet's tail.
I guess a good example of what we're seeing with the tail would be like boiling a jug and seeing the steam coming off it, and that steam has been illuminated by sunlight.
Effect, so you could. if without the illumination, it's very hard to see the steam coming off. You get it into that shaft of sunlight, and you can see the steam. But again, the steam is compared to the vacuum of a comet's tail. The steam's really thick compared to the comet's tail. But yeah, that's a very good analogy.
Right. Now, in your Astroblog, I'm just going back to that screen now. The question is raised, but what about meteors? Will there be a meteor shower then? So,
sadly, tragically, no. The problem with first-time comets is that there's very little material coming with them. Now, Hollywood would have you believe that comets are associated with these giant clouds of big, chunky debris. It's not true. Comets, as they pass around the sun, do release dust and other debris. Most of that debris is about the size of a grain of sand. Some might even be as big as pebbles. But it's also released in a very narrow band. Now, you know that several comets, several meteor showers, are all from comets. Comet Halley is associated with the Orionids. The Leonids are associated with debris from a comet, and so on and so forth. But these trails have had a long time to disperse from the comet as it went around. For example, when we're seeing the Orionids, we're often seeing clouds of dust and material that were released centuries ago. And it takes time to build up these masses of dust that are big enough to actually intersect Earth's orbit. And we've had a lot of relatively new comets, not inverted comets, we've had a lot. We've had a number of relatively new comets come through reasonably close to Earth, and not one of them has produced a meteor shower because the debris trail is not big enough to intersect Earth's orbit. Now, remember that we saw the tail in our simulation. Simulation is still here, so I'll go back to when it crosses our orbit. Okay, so there's the comet crossing the orbit. I'll try and zoom in so you can see it a bit more. Okay, so there's Earth over there. There's the comet crossing the orbit there. And as you can see, we'll just rotate it up. You can see the comet's well above the plane of Earth's orbit.
Right, so the red cross there is marking Comet ISON.
Yeah, and the other comet is Comet Encke. Don't worry about that one.
Okay, we see another comet out there to the right, so that's Comet Encke.
Yeah, that's Comet Encke.
Now, this is actually an interesting point too, isn't it, Ian, that most people are not aware that at any given time, certainly at the moment, there are more than 200 comets in our solar system.
Or within the inner solar system.
Right.
So there's about there's well over 250 comets we know about. Of those, about something a bit over 200 comets are periodic comets that are all fairly close in, and then you have comets with much longer orbital parameters, of which at any time there'll be about a dozen or so of these floating about. But unfortunately, most of them don't get very bright. But in any given year, you'll often have one or two that are bright enough to be visible in binoculars. In this case, this year we've been very lucky. We've had two that were binocular visible. That was Comet Lemon and Comet Pan-STARRS. Encke may get bright enough to be visible in binoculars, but it's also going to be very low down in the horizon in the murk. Northern hemispherians might be able to pick it up fairly easily. And we've also got another comet, yet another Comet Lovejoy, C/2013 R1 Lovejoy is coming in. And it will be, it might get bright enough to be visible in binoculars too. So we've had a bit of a bonanza of bright comets. I should explain to your listeners, to an astronomer, a bright comet is anything that's brighter than magnitude 12. The brightest that a person with good eyesight the brightest object in the sky that a person with good eyesight can see. is between magnitude 6 to 6.5 if you're under really dark skies. So what astronomers call bright comets to everybody else are really amazingly dim. And we get excited if the comet gets bright enough to, say, about magnitude 8, and you can see it in a set of binoculars. We get really excited. So you can imagine, with Comet ISON potentially getting up to quite significant brightness, you can see why all these amateur and professional astronomers are getting really, really excited. And so, so we've got Comet Encke there, next to Comet ISON. But the point the point is that Comet ISON is looks brighter because if we just move this down, Comet Encke is actually closer to the sun than Comet ISON is at its time. But the major point here is to see that ISON is well above the plane of Earth, and any dust and material that's coming out of that's coming through the comet's tail is going to miss Earth's orbit by about 10 lunar diameters. The distance between the Earth and the Moon. If you take the Earth to Moon distance, the closest that the comet comes to our orbit is 10 times the distance of the Earth to the Moon. So that's pretty far away. And because it hasn't been around the sun more than once, the only material associated with it is the material in the tail. That's fairly narrow. And again, also, as we saw, I'll go back to the animation here. I'll just run the animation. As we saw, the comet's tail follows the comet around the sun. And by the time we get to Earth gets to where the comet was, all the material in the tail has been gone long ago. Now, there was a statement from on the NASA website about a meteor shower from ISON several months ago. The NASA PR people should be hit up the side of the head with a very large book of astronomy, because what they were talking about was noctilucent clouds, where very, very fine cometary dust gets blown into the upper atmosphere of Earth and can form very thin, high-level clouds which have a rather beautiful colour. But that's not a meteor shower. A meteor shower is a lump of something that's coming in at several kilometres per second and burns up in the atmosphere. We won't get any of that. We might get noctilucent clouds, but looking at the orbit and looking at the simulations, it's possible to get a little bit of dust, but nothing spectacular, and no meteor showers as meteor showers.
From looking at the trajectory of Comet ISON, it certainly seems unlikely that we will see anything as a result of it passing through. Now, another interesting point about all of these other comets that are in our solar system is we say that there are over 200 in our inner solar system. Now, would the average size of the nucleus of the comet be fairly similar, or are they quite small?
There's a range of sizes. The largest comet that we know of, it was Comet Hale-Bopp, with about a nucleus diameter of about 60 kilometres. The majority are much smaller, ranging from Halley's Comet, which is about 15 kilometres, down to between 3 to 1 kilometre. The Kreutz-Sungrazer comet stream are generally in the size of half a kilometre to 200 metres. So you have this broad distribution with a very few bigger comets to lots and lots of little small comets. It's a power law. We have lots and lots of small comets, a few medium-sized comets, and a very few large comets.
Right, and where would you say that Comet ISON fits into that range?
Okay, from measurements that the infrared telescope Spitzer took of the dust production from Comet ISON, and from measurements that Hubble has taken of Comet ISON, the diameter of ISON's nucleus, that's the solid lump of ices and dust in the centre, is probably around about 4 to 5 kilometres in size. That's actually an upper limit. It's possibly smaller than that. So it's a pretty average sized nucleus for a comet, around about 4 to 5 kilometres.
Right, okay. Now I'm just wondering, have we got some more simulations to share, or should we go back to the camera at this stage?
Well, depends what you want to see. Those are the orbital simulations that I have, but you might possibly want to see simulations that I've done of the comet as you would see it in the evening sky.
Right, let's take a look at those.
I'll just locate where I put that. So I'll pop this up full screen, and this is the view from Australia and from New Zealand. So this is very southern hemisphere biased. As you're a New Zealander, you may appreciate this. But what I've got where Comet ISON is now. If you would get up at 5 o'clock in the morning and look out, Comet ISON is just below Mars, but it's faint. It's somewhere between magnitude 11 and magnitude 12. This is, again, as we said, this is what astronomers consider bright. We get really excited about this. And I'll give you an idea of how it's going to evolve over the coming days. And I'll start.
So currently this is the 17th of September.
Yep, and now I'm going to go forward in 1 day steps. And you see the comet's staying relatively dim, because as we go forward in time, of course, being the southern hemisphere, we're going from autumn to spring to summer. Sun rises earlier and earlier. Just give me a moment. I'll put this into. I'll just change the time so we can. So, okay, Comet ISON at this time is about magnitude 10, not very bright still. And this is in the first days of October. And for the southern hemisphere people, Comet Encke is down there. If you're in the northern hemisphere, Comet Encke will be reasonably well placed. But I'll just keep zooming forward. And now the comet's rising high in the sky. We're now in mid-October. The comet's magnitude 8. You can now see it in binoculars. I'll change the time to...
So this is currently on the 20th of October.
This is currently on the 20th of October. It's just gone into daylight saving time, so I've had to adjust the daylight saving time. So the comet's magnitude 8. And now it's starting to get brighter and brighter. It's also you'll also see Comet Lovejoy coming in up to the top left of your screen, and the bright asteroids Vesta and Ceres. There's Vesta there at magnitude 7.5 and Ceres at magnitude 8. Comet ISON is now magnitude 5, so you should be able to see this with your unaided eye. You don't even need binoculars. It's fairly low to the horizon, but it's still bright enough to be seen with the unaided eye in the early twilight. Now, in this simulation, this doesn't have any tails attached to it, but it still gives you an idea of what and because this is pre-dawn, pre-perihelion in the pre-dawn, we don't expect to see a very big tail. And now you can see the comet's getting brighter and brighter. It's quite. It will now be quite easy to see, and it's getting closer to the bright star speaker until we're getting to. This is the. We're now well into November. This is the 18th of November. The comet's now really quite bright. You'll be able to see it quite easily with the unaided eye, and it'll be quite close to the bright star speaker, so it'll be very easy to see. You go out in the early morning. If you look off, look east. If you look off to your left, you'll see bright Mars over here, quite bright at about magnitude 1.4. Then speaker again bright at just over magnitude 1. And then Comet ISON is about magnitude 3, reasonably bright, and should be easy to see next to speaker. It should be quite really interesting in the morning. And now it's getting rapidly brighter, but it's also getting further and further into the twilight. In comparison with, if you remember, Comet Pan-STARRS was about as bright, got to be about as bright as magnitude 1, but it was really low in the twilight. This is a lot higher in the twilight, and so you'll be able to see it reasonably easy. And then as we're coming up to this is the 22nd of November, getting close to when it's supposed to be going around the sun. But as you can see, it's getting very close to the horizon, and it will get harder and harder to see. At this time, the tail might be getting a bit bigger, so it's entirely possible you'll be able to see the tail rise above the horizon before you see the comet. And now it's really quite bright, relatively easy to see, but it's going to be very low to the horizon. So if you wait until it gets gets a little bit higher, the sky will be bright, but you should be able to still see it reasonably well up to half an hour before sunrise.
Right.
Right.
Okay.
And then within the next couple of days, it'll rapidly rush around the sun. And for us in the southern hemisphere, that's a lot. It stays below our horizon for. The comet itself stays around below the horizon for the rest of the time. Now, this depends on what the tail looks like. It might be entirely possible that after the comet whips around the sun and comes back out on the other side, even though the head of the comet from the southern hemisphere is hidden below the horizon, we may see the tail poking up over the horizon and looking quite nice in the first few days after it's come closest to the sun. For those people in the northern hemisphere, I'm going to change the simulation to the northern hemisphere. I'm going to use Roswell, New Mexico. And I have to change the time. So the comet is quite bright, but it's also deep in the twilight, even from the northern hemisphere. And then it'll zap around being really bright, and then emerge from the sun. I'm going to you'll see it coming screaming out from below the horizon, really bright, and there should be providing the again, this is all providing that the comet doesn't do a comet lovejoy on us and completely disintegrate, in which case we may just see a tail and not much else. But hopefully the comet will remain reasonably intact, and we'll have a relatively bright comet and a nice tail coming up there. So that's the view from the northern hemisphere. For us from the southern hemisphere, I'll go back to Adelaide.
This is Stellarium, by the way. If anybody wants to use this software, it's actually free software. Just go to stellarium.org and you can download it for free.
Yeah. And we'll go to 5 o'clock in the morning. And 5:30. And Comet ISON's down in there somewhere. It'll be almost impossible to see from Australia and New Zealand. You might be able to see it a bit from the equator, but for those of us that are down for the equator, once the comet's gone around the sun, it's below the horizon, but you should see the tail sticking up. Right, of course, the bad news is for people from the northern hemisphere that to see the comet at your best, you have to get up at about 5 o'clock in the morning. Not much fun.
Mm. But hopefully will be certainly worth the effort.
Yeah.
Okay, now also covered in your blog, Ian, are the questions about the possibility of earthquakes and solar flares as a result of this comet. What's the likelihood of that happening?
Absolutely none at all. We had the same sort of thing happening with Comet Ellen a couple of years ago. Comet Ellen was going to cause all these earthquakes. We'd have massive disruption. Nothing happened whatsoever. It zipped past the Earth with no effect and then quietly disintegrated. The same thing happened when Comet Lovejoy went past. Nothing happened. Notably, there seems to be a lot more panic when comets are coming in from the northern hemisphere. When Comet McNaught came past back in 2007, and this was another comet which was visible in daylight. Again, if you were very careful and blocked the sun out with a building and looked very carefully, you could see it in daylight. It had this amazing, for weeks, there was this brilliant tail across the sky. It was fantastic. And there was not a single person saying it was going to cause earthquakes or hit the sun or do anything like that, even though it was pretty similar in what it was doing to what Comet ISON is. So for people to be worried about earthquakes, it appears to be the comet has to be a northern hemisphere phenomenon. But trying to get the scale of things. A Comet ISON is basically a 5 kilometre wide ice cream sundae. We have just above us a rather large lump of rock called the Moon, which orbits us and actually raises tides in our crust. The gravitational force of the Moon is sufficient to raise a gravitational tide in the crust of Earth. So you'd expect that if the gravitational force of something like a comet was enough to cause earthquakes, then the Moon would cause earthquakes in spades. It doesn't. It actually does increase the probability of a very rare form of shallow earthquake by about 1%, or maybe about 5%. So if the Moon can't cause massive earthquakes, then a oversized ice cream sundae isn't.
Right.
And we've had comets come closer to us. We've had comets come a couple of lunar distances away, and they've done absolutely nothing. And Comet ISON comes nowhere near us compared to some of these other comets. So we've had close cometary encounters before. Nothing happened. We had Comet Elenon. Nothing happened. So Comet ISON won't do anything. Right. When it comes to causing solar flares, again, consider that Comet Elenon is an oversized ice cream sundae, and the sun is enormous. It's incredibly enormous. It's to imagine that Comet Elenon, the Comet ISON can cause solar flares is, well, imagine dropping an ice cream cone in the centre of Australia and expecting it to start a tornado.
Right.
It's not going to, as some people will say, what about the electric fields? Comets don't actually have electric fields. They're pretty much electrically neutral. And the electromagnetic field of the sun is many times bigger than that of the comet. The comet can't actually do anything to it. But again, all these theoretical considerations aside, we've already had comets that have been bigger, have come closer. And we've had the great comets of the 18th century, which whipped around the sun closer than ISON. We've had Comet Lovejoy, which whipped around the sun closer than ISON, and nothing happened. So Comet ISON has the potential, if it doesn't disintegrate, to be a really beautiful comet. It may be better than Comet Lovejoy, which will make me very disappointed because I won't be able to see it. But in terms of what it can do, people forget the scale of the universe. The scale, even of the solar system, is really big. And again, to get the sense of proportion, as I said, it's like dropping an ice cream cone in the middle of Australia, in the middle of outback Australia, and expecting it to set up a tornado which will then go and rip into the United States. The scale it just doesn't work.
Right. And I think the other point that we have to keep in mind too, is, as we mentioned earlier, is that we currently have hundreds of comets in our inner solar system. But of course the focus at the moment, everybody is thinking of Comet ISON, and as you say, 2 years ago it was Comet Elenin. But people overlook the fact that there are hundreds of comets out there. There are even more asteroids out there, and certainly the solar system is a big place, and these objects are tiny in comparison. You mentioned the effects of the moon, and obviously with the moon we have the ocean tides, and you've mentioned a crustal tide as well that many people are unaware of. But the fact is that if the moon would cause earthquakes, then I think it's fair to say that we should expect to see a great peak of earthquakes, a tide of earthquakes every full moon and every new moon, when the sun, the moon and the earth are almost in a straight line. And certainly that would be so during a total lunar or total solar eclipse. Would you agree?
Yes, and we see nothing. We've got over 100 years of continuous earthquake data, and there is no peak in earthquakes at full moon or new moon, and there is no peaks when you have total solar eclipses or lunar eclipses. So there's no association. And again, as you say, there's lots of comets out there, and we've had comets come closer to us, we've had comets come closer to the sun, we've had bigger comets coming closer to the sun, the great comets of the 19th century, we had a whole bunch of them, and nothing happened. Absolutely nothing happened. So Comet Elenin is a really exciting comet.
Comet ISON.
It's ISON, yes, I'm sorry. I've got Ellen in the brain.
Yes, yes.
Comet ISON's a really exciting comet. It's one of the few Oort cloud comets where we've had a sufficient warning to get lots of observation with professionals, with amateurs, with spacecraft. Interestingly, the last time this happened was Comet Kohoutek. And we had this mass of observations occurring by amateurs, professionals. They had balloons going up. And we've got a wealth of data. And now with Comet ISON, we're repeating this, but we've got so much better. When Comet Kohoutek came around, we had film cameras, and the amateur astronomers' equipment was nowhere near like it is today with CCD cameras. Many of the amateurs, many of the average amateurs have equipment that is equivalent to what was professionally available back when Kohoutek came around. We have more spacecraft pointing at this thing, and we'll get this wealth of amazing data about a comet from the deep freeze of the Oort cloud. So it's scientifically really exciting.
So in summary, we can say that there's certainly nothing to fear with Comet ISON. In fact, it's something to be looked forward to, and hopefully it will be an event that we can remember for the rest of our lives.
Oh yes, very definitely so. It will be, even if it fizzes like Kohoutek did. Let me say fizzes in inverted commas. Even if it fizzes like Kohoutek did, it'll still be a nice comet. It'll still be good to observe. It may not have a tail that stretches over most of the sky, but it will still be a beautiful comet to observe, even if it fizzes. And so we have a choice. We have something that will be nice or something that will be fantastic. And we should be excited about it. We should not fear it in any sense whatsoever.
Okay, so thank you, Ian. Just in closing, we're just looking at your Astroblog page again. This is astroblogger.blogspot.com.au. So I encourage people to go and check out your blog, and I will put a link in the description area. And thank you very much, Ian, for your time. It's been fascinating talking to you.
It's been a pleasure.
Thank you. And as always, do check out my Facebook discussion page, Voices of Reason to Explain X, or VORTEX. I'll put a link in the description area. Thank you for watching.